This is actually sadly a tragic example of a mass panic in, I think, some 20 years ago or so in an English soccer stadium, where sadly I think almost 100 people died. We can safely assume that like every one of these agents was individually safe and aligned in the sense of they didn't intend to harm anyone and they did the best they could, while weren't able to cooperate in a way that they could prevent this disaster. We are at the end of one very short era where AI systems, advanced systems, were mostly deployed in kind of single user settings and didn't interact massively. And we're at the dawn of like this potentially much larger era where we have multiple agents interacting on a massive scale. One of Palantir's products, which is basically a chatbot interface that tells you what kind of actions to take on the battlefield. So have like a direct link between recommendations given by an LLM agent and what might happen in a war situation. So what's different here compared to regular AI systems and the risks that come with them? The simplest way to think about it is to think about interactions as a new source of harmful, unforeseen results. This is something that we know already. A famous example is the 2010 flash crash that some of you might have heard about. This graph here, this was an event where a large sell order, a regular event in the market, triggered some automated trading bots to sell and basically squeeze liquidity out of the market and completely crash the S&P 500 futures market on that specific day, leading eventually to the shutdown of all trading. Let's quickly talk about why multi-agent AI risk might be different. When we talk about a single AI safety, a single AI agent being safe, we usually understand this as it being robust and aligned, so it doesn't fail in stupid, unintended ways, and it acts according to the objectives given to it by its principal, as we say, the user or the person deploying the system. This is a hard problem in itself, and I would argue it's far from being entirely solved. It's definitely necessary for safety on a larger scale, but it turns out it's not sufficient. The reason is, as I've already pointed or hinted at, that there are just fundamentally new risks emerging from like interactions at a large scale. To give just a couple of examples, if you have errors or biases in isolated systems, they can be horrible or insignificant in isolation, but could compound disastrously. These, I think the flash crash might be considered an example of that. Groups of agents can develop dangerous capabilities or goals that you don't find in individual agents. I'll also show an example of that. And then maybe very fundamentally and quite simply, the different people involved in deploying these systems might have conflicting interests, and that can itself be a source of risk. This is actually sadly a tragic example of a mass panic in, I think, some 20 years ago or so in an English soccer stadium, where sadly I think almost 100 people died. We can safely assume that like every one of these agents was individually safe and aligned in the sense of they didn't intend to harm anyone and they did the best they could, while weren't able to cooperate in a way that they could prevent this disaster. Similar things can happen in AI systems, of course, as well. Now, of course, you might raise an objection. We have multi-agent systems of intelligent agents. In fact, we have like billions of highly intelligent agents interacting with each other every day and since decades. It's called human society, and it's been going all right. Or maybe we can argue about this, but why the big fuss? What's different? And I would say that there are a couple of key differences that should make us think harder about the AI case and take this maybe more seriously. Some of these are quite simple to understand. So AIs just have some qualitative differences that may make a huge difference to the risks that they're posing if deployed at a massive scale. One being the speed at which they're interacting. So the little screenshot here shows the output from the Grok LLM accelerator that puts out, I think, 300 tokens per second for a fairly advanced model, which is, of course, much faster than the rate at which I'm producing tokens at the moment. This is just a snapshot in time. Probably this number grows by a factor of 10 every year or so. Interaction rates between these systems are, I think, expected to be much faster than anything we've seen on human scales. The scale of deployment will also be probably much larger than what we see in human societies. The next big factor, I think, is replicability and adaptability. whereas humans adapt and evolve on like relatively slow timescales. So with, I guess, cultural evolution on the order of decades, and then biological evolution much slower still. AI systems can be replicated and adapted at a much faster rate, and there's huge economic incentives to make them highly adaptable and faster at evolution. So any equilibrium that you find in these systems can be much more brittle just for that reason as well. I've already mentioned the communication aspect. Clearly, AI systems can communicate much faster and could potentially communicate at much higher, I guess, bit rates, could communicate over channels that are not seen in human societies, which could also mean that the communication is more opaque and we have a harder time modeling the intentions and communication of these agents. And finally, there's like a slightly technical point that I will maybe come back to if we have time, is that these agents may have, I guess, like academically said, you say very different affordances for commitment. So the way in which they can build trust or commit to certain actions could be fundamentally different from the way that humans do it. And this has, as is discussed in the report and at length, I think, has both positive and potentially negative consequences. So it's an interesting point that we may get back to later. Let's get into it. This is the core of it, basically, the taxonomy of the multi-agent failure modes. This is the way that we organized these different cases in the report. And it's based on the overall structure of incentives in the system. So the first question we ask is, are we in a situation where cooperation between these agents is desired or not? And if it's desired, do all the agents have identical or almost identical objectives, or do they have only partially overlapping objectives? And based on these two questions, we find basically three different categories of failures that we can use to systematically study these different cases. The first is when we have cooperation being desired and the objectives being almost identical. If we still find failures in this case, then we can call it a miscoordination. So it's a failure to work together effectively despite everything else being right, everything else being shared objectives. The next case is when we actually do desire some cooperation, but the agents do not share all of their goals. So they might have some common goals, but they will also have some selfish interests. In this case, we can have conflict. And then the question is, do we get what is called Pareto optimal outcomes, meaning that despite these differing objectives, we can negotiate and find the best common solution, even if that means everyone kind of cutting down on some of their selfish objectives. And the last case is when we don't even want cooperation between the agents. And this is what we call collusion, which is when agents cooperate despite it being undesirable or harmful. Let's go into these for a moment. The miscoordination case, which is defined as agents sharing an objective, but then failing to coordinate and realize the objectives. Here's a very simple example. It's a bit of a toy example, admittedly, but I think it has interesting generalizations. A shared objective in a fleet of autonomous cars might be to yield to an emergency vehicle when an emergency arises. So let's say we have a couple of autonomous vehicles on the road. There's an accident. It's in everyone's interest to make some space for an emergency vehicle and let it pass. This little case study or this little simulation that some people ran for our report basically showed that agents trained on different yielding conventions. So like we had some foundation models that were trained on different yielding conventions from different different nations basically failed to coordinate effectively on which side to yield to. And so despite this being in everyone's interest, the agents were just not capable enough to actually realize their shared objective. The underlying mechanism here, generalized slightly, is incompatible learned strategies and conventions. This can be as blunt as in the example that we just saw, but I would argue that it can also be much more subtle and could be much harder to detect. And so it is actually, despite this being somewhat of a toy example, this could very well be a very realistic case. Other cases in which this can arise are due to limits on communication between the different agents, or more generally a need for zero few-shot coordination. And then on the training side, if you imagine these agents being trained in multi-agent reinforcement learning setups, a fundamental mechanism that drives miscoordination here, or prevents coordination, I should rather say, is what is called the credit assignment challenge, that you typically in failure cases can't point your finger at any particular agent and say, hey, this one made the mistake and this one should correct its convention, but rather it just makes sense to talk about a failure in the context of the overall convention. And so unless this is pre-established, the teams of agents might just not be able to learn it. I guess the general context here and the challenge for people designing these learning systems, specifically if they are supposed to do online learning in the deployment environment, to actually consider the learning dynamics here and make sure that they can learn shared cooperation strategies even in the face of these hurdles. I would say that of all the failure modes that are discussed in the report, this one is maybe the one that is least worrisome in the longer run, because you could look at this as a pure capabilities failure and say that actually here in this case, everyone is on the same page, like everyone wants to achieve the shared objective. The fact that the agent doesn't, or the agents don't learn to coordinate and realize the shared objective is something that market pressures will correct by itself. Basically, people will learn to push forward these learning algorithms. Of course, that still needs people implementing it, but it's probably something that will somehow be addressed by future agents and like the more advanced capabilities that we should expect to see. The case of conflict is I think a bit more complicated than that. So here we have a more complex setup where we have what is called a mixed motive setting. The agents do have some shared interests. Like a very simple, maybe slightly cheesy example is every human has a shared interest in like preserving at least some aspects of our shared environment, keep it in a state that makes it possible to biologically survive. But we do also have selfish interests, such as taking some of the natural resources and just using it for our own purpose. So these are the mixed motive settings that we are talking about here. And the conflict in the lingo of our report is a case where agents fail to achieve Pareto efficient outcomes in these mixed motive settings, meaning they don't coordinate to achieve the best solution for all the agents taken together, but rather end up in situations where it would actually be better for them to change their strategies, but they just can't. So some classic examples are social dilemmas, the tragedy of the commons, races to the bottom, or escalation races, where it would be much better to, like, let's say, stop a war, but it's hard to do it in practice. And we have these problems in humans, of course, but we might have this same problem in agents and AI agents as well. Here's a very simple case study from the report that basically just shows that even relatively advanced AI agents that we can build nowadays are not by themselves, they're not magically good at this. So what was done here was to take a population of LLM-based agents and give them the task to jointly manage some shared resources, let's say fishery grounds or a shared river, and then measure the overall welfare, meaning the kind of the goodness of the outcomes that they achieve over many iterations of this game. And the result was basically that even the best models today, and even with like all the information about the context that they're in, do in a large number of cases, large fraction of cases, do not end up cooperating efficiently and actually end up depleting their shared resources, even though they're explicitly instructed to avoid that outcome. So here, again, like some slightly generalized technical mechanisms behind this. Resource over extraction is one thing that can happen here. We could expect such races and escalation to happen much more rapidly in the AI case because of this speed, maybe different and maybe potentially stronger biases, as well as like lack of human-like norms that could regulate some of these races. And I would add that unless the surrounding societal context is in place, the deployment of escalating agents might be economically incentivized. And this is actually something that I find quite worrisome. As long as we don't have like clear liability and potentially legal norms on what AI agents can do on our behalf, it might be very much incentivized to deploy maximally exploitative, maximally selfish AI agents on our behalf, which could make things much worse, of course, compared to the situation that we're in now. And finally, the third big category, collusion, defined as a secretive cooperation between agents at the expense of other agents, notably including humans, with the classic example being collusion to undermine market economics, meaning agents coordinating to set prices at levels that they couldn't achieve in a regular market and thereby harming the other market participants, which is, of course, also happening in human markets. But we have antitrust laws to prevent that to some extent. Some things to give us pause here are that it's quite plausible that collusion, which is already hard to detect in humans, could be even harder to detect in large deployments of automated agents. Also, there's some evidence that both tacit and explicit collusion is possible in AI agents, with tacit collusion being a form of collusion that doesn't require explicit communication between the colluding partners. An example of tacit collusion that we present in the report is an example from the German retail gasoline market, where in 2017 adaptive price setting algorithms were deployed quite widely. Subsequent research by economists has demonstrated that the adoption of these algorithms has increased the margins quite significantly in these markets, meaning that after introduction of these algorithms, consumers paid higher prices, basically, which these researchers interpret as evidence of collusion between these algorithms. So, and that's also supported by independent research on RL agents, where it's been shown that RL agents can actually learn colluding strategies, even without explicit communication. So that's an interesting case. And then the other case, of course, is the explicit collusion, which might be a problem in more advanced AI agents, where they could learn to communicate over channels that are just not legible to us. So that's the keyword of steganography, where agents hide their messages in messages that are on the surface just innocuous. The first reference here is the one that I alluded to. So RL algorithms can learn these collusive strategies by themselves. And so if we don't design our algorithms in a way that they do not learn this, if we deploy them and maybe they even do online learning, it's very plausible that this happens again and could also go undetected in the future. The other case of steganography also comes under the keyword of, which is like a fun word that some AI safety researchers use to basically point to the possibility that if we endow future agents with, let's say, direct latent space to latent space communication capabilities, which could be, again, economically incentivized, we might just not be able to detect what they're actually communicating about effectively, and thereby open us up to collusion that we can't oversee. And then the last point that I wanted to point to is that a lot of the oversight mechanisms that people have in mind for controlling very advanced agents basically rely on other agents reading the thoughts and actions of these advanced agents and giving us signals as to whether they are safe or not. And quite clearly, if there's collusion, if collusion is possible between AI agents, then this is not by itself a safe strategy. You need to make sure that there's no collusion between the overseer agent and the agent being overseen. Also quickly wanted to point to a recent paper by a team from our lab that looked into the capabilities of current language models on the steganography front, which I should add, they're still quite limited at this point. So they can execute steganography if explicitly instructed, but the finding in this paper was that they cannot yet pick it up easily by themselves. But I think the evidence from these other RL experiments is strong enough that we should expect this to emerge quite naturally for future LLM-based agents. The content for today's talk it's a big report that came out at the end of February this year. But the organization that I'm directing, Apart Research, had a quite specific input to this report. Namely, we organized a research hackathon, which is what we do for a living, basically, on multi-agent safety problems. And we had around 150 participants for this event, all kinds of backgrounds, technical people from research and engineering. Around, I think, a bit more than 20 teams handed in what I would call research MVPs, so little write-ups on experiments they ran. And quite a number of those MVPs actually ended up directly included in the report as one of the case studies. Apart Research runs these research hackathons. We're essentially a decentralized AI safety research lab with team members from basically every time zone, from Singapore over Europe to the US. We try to nurture top research talent in AI safety and get people to actually get to action basically on the research and support them to execute the most interesting research projects that come out of these events.